Hi everyone, myself Dr. Arun from RMK College of Engineering and Technology. Today we are going to discuss about pulse code modulation. This is coming under digital communication. So within that baseband communication system, in this video detailedly we can discuss about pulse code modulation. Outcome of this lecture, at the end of this session you will be able to understand the importance and operation of pulse code modulation. So outline of my presentation starting from objective of pulse code modulation, block diagram of PCM, process of PCM standards, bitrate and bandwidth in PCM, advantages and disadvantages of PCM and applications of PCM. Next objective of PCM is pulse code modulation is a method used to convert analog signal into digital signal. So your input is analog signal that will be applied to pulse code modulator or analog to digital converter. The output will be in terms of digital nature. This process done at your transmitter side. Receiver side input is digital, the output is analog. Naturally all the signals are only analog signal. For our convenience we are converting analog signal into digital signal. So here this analog signal is applied to your sampler, you are getting the sampled output. Then you are applying to your quantizer, your sampled signal is quantized or performing the roundup process. Then based on each and every sample amplitude you are getting the encoded output like this. So the three steps available, the first one is sampling, second one is quantization, the third one is encoding process. In this particular slide representing the entire block diagram of pulse code modulation. In this entire block diagram, the first one is your information source. The output of the information source is continuous signal. I am assuming the audio signal, the frequency range is 20 Hz to 20 kilohertz. This 20 kilohertz signal applied to low pass filter. What is the use of this low pass filter? It is used to eliminate the aliasing effect. Before performing the sampling process, we are going to identify what is the maximum frequency of your audio signal. Here as per this particular example, 20 kilohertz is the maximum frequency of the audio signal. So this low pass filter will allow 20 Hz to 20 kilohertz. So if the frequency is maximum allowed frequency is 20 kilohertz, the sampling rate requirement is 2 into 20 40 kilohertz. So if you are allowing more than 20 kilohertz through this sampler, finally the sampling theorem will fail. The consequences you are not able to get a original output signal with acceptable quality. So if you want acceptable quality, you should not allow more than 20 kilohertz signal towards your sampler. So this entire process, entire block diagram representing the transmitter. So the transmitter consists of low pass filter, sampler, quantizer and encoder. The next one is this is your channel part. The channel part after transmission, if the signal is traveled to long distance, the attenuation will be more, then your signal strength will be reduced, that will be strengthened by using repeaters. After a number of repeaters, finally it reaches to receiver. This receiver consists of decoder, reconstruction filter and the final destination. So your output will be your sine wave or your audio signal. So your continuous signal is applied here. Finally here binaries are the output, then here the final binaries are the input. So next here we are getting the analog signal. Next this will explain the entire process of pulse code modulation. So here the same block diagram almost. So here the continuous signal, analog signal is available. So I would like to explain this entire block diagram with one application, that is called your telephone line audio communication application. So here continuous in time, continuous in amplitude. This is your continuous in time and also continuous in amplitude. So the maximum frequency of the audio signal as per telephone line is 4 kilohertz. This 4 kilohertz signal will be applied to your sampling process. The sampler will sample your signal. After sampling, your continuous wave will be converted as discrete. So if you are going to perform this corresponding sampling process, you have to satisfy this sampling theorem. Fs is greater than or equal to 2Fm. Fm representing your message signal frequency. Here the message signal frequency is 4 kilohertz. So that's why the minimum sampling rate is 2 into 4, totally 8 kilohertz is the minimum requirement to sample your information signal. As per this particular example, 1, 2, 3, 4, 5, 6, 7, 8, 9 samples are available. So in this 9 samples are applied towards your quantizer. So in this quantizer, what is the objective of the quantizer means? In your sampling, discrete in time, continuous in amplitude. Discrete in time but continuous in amplitude. What is the meaning of continuous in amplitude means? Each and every sample based on the actual value of your message signal, in your instant value of your amplitude of your each and every sample may be 1.1 or 1.2, 2.5 like that. That 1.1 will be converted as 1 and also 2.2 will be converted as 2. So like that, if you are performing the roundup process, that is called your quantization process. So after quantization, your discrete time, your signal is discrete time on and also discrete in amplitude. So then number of quantization levels required for telephone voice communication, at present we are using 256 levels. So number of samples is 8000, number of quantization levels is 256. What is mean by number of quantization level means each and every horizontal line representing one quantization level. This is the standard amplitude and also your standard interval. They are specifying as your quantization levels. Each and every quantization level representing its own voltage. So 0 volt to maximum they are representing approximately, I am specifying as suppose 5 volt. So that 5 volt will be divided equally and specified as quantization level. So that quantization level used to round up your corresponding sampled value. After roundup process, each and every sample or quantization level having equivalent binary. So that quantization level will be represented by using binaries. That binaries representing the corresponding value of the sample. That corresponding binaries are released by encoder. So each and every sample will be passed through this encoder. Finally you are able to get a digital output. So your input is analog. Afterwards, by applying towards your sampler, your output of the sampler is discrete. Then we are quantizing, that means performing the roundup process. After that you are getting the digital output. So your input is analog, your output is digital. So your whatever may be the sine wave is available here, your same sine wave represented in terms of binary. So here one example animation is available to understand your pulse code modulation. Your information signal is sine wave is available. So the sine wave is first we are going to perform your sampling process. After sampling you are getting the 6 samples here. After sampling we are performing quantization process, each and every line representing quantization levels. Then after your quantization process, here red line representing the quantization process. That means, for example, here I am going to take the second sample value is 7.4. So after quantization, that 7.4 will be converted as 7. That is, in between these two lines the sampling is falling. So that's why we are going to round up the nearest value. So 7.4 will be converted as 7. Here actual value of your message is 7.4. I am rounding the process for my convenience as 7. So that's why it will create a corresponding or degrade the quality of your message. That means 7.4 is the actual voltage. So that will be converted as 7. So 0.4 is the quantization error. 0.4 is the quantization error. Each and every quantization level will be represented in terms of your binary. If the number of quantization levels increases, the number of binary requirement will increase. This will represented as 2 power V. So V representing how many number of bits required to represent all quantization levels. Here this example consists of 16 quantization levels. 2 power 4 equal to 16. 16 quantization levels represented by using 4 bits. So then after quantization, we are going to perform your encoding process. You can see this animation. The first sample, I am considering this is the first sample. In this first sample, the corresponding binary is 1011. So the output of the PCM is 1011. The second sample is 1001. So the second sample output is 1001. So similar manner, each and every sample, the corresponding binaries are released. Finally, your entire sine wave will be converted as in terms of binary format. That means your analog to digital conversion process we are performed. So in this slide we are going to represent your pulse code modulation standards. Sampling rate represented 8,000, 11,000, 16,000, 8,900, like that. If the sampling rate is increased, your quality of the signal will improve. So your 18,000 to 48,000, the same audio signal processed, but the quality is in 8,000 samples per second, the quality is less. But in your 48,000 samples, the quality is very high. So if based on the requirement of any communication system, you can improve the corresponding sampling rate, you can improve the quality of the signal. So here we are representing bitrate and bandwidth requirement for PCM. If you want to transmit your audio signal by using your pulse code modulation, how to calculate the bitrate and your bandwidth. The sampling rate Fs is greater than or equal to 2 FM. Your Nyquist rate is the minimum sampling rate. Fs is equal to 2 FM. Here FM representing your maximum frequency of the message signal or audio signal. Number of quantization levels represented as Q is equal to 2 power V. V represent number of bits per sample. Q represent number of quantization levels. By using this particular two parameters, we are able to calculate your bit rate. Bit rate R is equal to V into Fc. V represent number of bits per sample. Fs representing number of samples per second. If you are multiplying together, you are able to get bit rate. So by using this bit rate, we are able to calculate bandwidth of the pulse code modulation. Bt is always greater than or equal to 1 by 2 into R. That means at least 50% of your bit rate. 1 by 2 bit rate is the bandwidth of. In this example, we are able to understand how to calculate bit rate and bandwidth if you are performing pulse code modulation. So in this example, we want to digitize human voice. What is the bit rate? Assuming 8 bits per sample. So generally human voice, the maximum human beings are able to generate 0 hertz to 4000 hertz. That means approximately 4 kilohertz. So that's why in telephone lines the maximum frequency allowed is 4 kilohertz. So sampling rate and a bit rate are calculated as follows. The sampling rate as per sampling theorem, 2 into your frequency of the message signal. That means 4 kilohertz into 2. So totally 4000 into 2, 8000 samples per second. You can imagine 8000 samples per second is required for human being voice with low quality. Then bitrate is multiplied with 8000 into 8. This 8 representing how many bits per sample. So totally 8 into 8000, 64,000 bits per second. So that means 64 kbps they are represented as bit rate. The bandwidth requirement is equal to 1 by 2 into bit rate, totally 32 kbps is required. To improve the overall quality of your pulse code modulated signal, that means in your receiver side you are expecting very good quality of the signal. So what are all the changes we have to perform to achieve that high quality means, if you are first point representing, if you are increasing the sampling rate, that means always satisfying fs is greater than 2 fm. If you are satisfying greater than 2 fm also, the quality of your message signal will increase at the receiver end. And also increase number of quantization levels, it will reduce quantization error. Then the accurate reproduction of your signal will be there at the receiver side. Increasing sampling rate and quantization will demand more bit rate and bandwidth. This is the trade-off in pulse code modulation. If you want more quality, sampling rate you must increase, quantization levels you must increase. Finally, you have to sacrifice higher bandwidth. Advantages of PCM, it is robust against noise and interference. That means the noise is a randomly varying signal, but in your pulse code modulation, the restricted amplitude is there to represent your 0 and 1. So then identifying your noises within this particular signal is very easy compared with analog signal. So that's why they are specifying it is robust against noise and also interference. Uniform transmission quality, that is the second point. The efficient signal to noise ratio and bandwidth trade-off is there. It provides secured data transmission. So we are able to add some additional encryption algorithms or encoding techniques to improve the security of the communication. It offers efficient regeneration. If you are transmitting for the long distance, so you are able to boost up your signal by using regeneration technique. It is easy to add and drop channels. You can add n number of channels, and also you can drop the channels by using your pulse code modulation. So this is specifically applicable in time division multiplexing. Disadvantages of PCM, large bandwidth is required for transmission. Compared to analog communication, there is the major disadvantage in entire digital communication system. The large bandwidth is required for transmitting your signal. More attenuation, obviously it will not travel long distance. The regeneration is required. So at frequent stages, the difference between original analog signal and translated digital signal is called quantization error. That means quantization error is more in pulse code modulation. If you want to reduce the quantization error, we have to improve number of quantization levels. Encoding, decoding and quantizing circuits of PCM is very complex. This is another disadvantage. PCM. Then applications of PCM, it is used in telephone voice communication, it is used in compact disc, PCM is used in satellite transmission also. Thank you for watching this video. We will meet again with another one topic.